Okay.
All right, next up we have Jonah Miller, who's going to share with us some low-level tricks and share his high-level vision for performant neutrino transport. Take it away, Jonah.
Yep, great. Thanks, Zach. And Zach, this talk is going to be a bit of a grab bag. Oh, well, first I have to show you this legalese. It doesn't matter. You don't have to worry about it. Right. So this talk's going to be a bit of a grab bag. The middle part of the talk, which is hopefully going to be most of it, is going to be low-level details of Monte Carlo transport, since I know this is something that the collaboration is interested in implementing in the Einstein toolkit. And so I'm going to give you some thoughts that I have about lessons learned, things that we've hit, that we've had to deal with, this kind of thing. But before that, I'm going to speak about the astrophysical motivation for why you might care about doing transport well. And this includes, because I can't resist, some recent work by I and my collaborators that I think really motivates why you want to have a detailed picture of the neutrino field. And then at the end, I'm going to close out by some ideas about what other kinds of transport strategies one might employ. I know you've already gotten some of that in the workshop. For example, the guided moments formalism and the M1 discussions that happened earlier in the week and today. Guided moments is particularly exciting in my opinion, so I'm really excited to see that work and hear that you all are interested in it. Also, I apologize for not being there in person. I wish I could join. Unfortunately, I wasn't allowed to travel given the current government crackdown on science, but I'm at least happy to be here and participating virtually. All right, so let's get started. So you've all heard about this story many times, but I wanted to introduce it just for those of you who may be new to the field, give you my picture. So at the end of stars live and die in binaries. And so after they've died, you may end up with two neutron stars, the cores of dead stars. Over a long time, the emission of gravitational waves decays their orbit until they get close enough that they merge, like in this picture, this movie here on the left. And when they merge, much of the material is streamed out in these tidal tails in the Lagrange points. Some of it becomes gravitationally unbound immediately and expands away in sort of an expanding donut. The remainder accretes back onto the remnant in the disk that forms here. And on the right here, I have a cutout of what this might have looked like for the 170817 event, where now I've replaced the central remnant with a black hole instead of a neutron star. There's the tidal ejecta in this expanding donut in this cutout on the far and then there's this disk that is driving a wind in this hourglass shape off of it more vertically than equatorially. I've labeled these neutron rich and neutron poor. These are really relative. The tidal ejecta is relatively neutron rich. The wind is relatively less neutron rich, but both are more neutron rich than symmetric matter. The neutron richness matters because of the process rapid neutron capture nucleosynthesis, or our process. And to show you how this works, I've got a periodic table, but in a funny way that you may have not seen before. So the x-axis here is neutron number, and the y-axis is proton number. And the diagonal here of solid dots, this is the symmetric matter and stable matter that we know and love. This is the normal periodic table. Everything else is an unstable isotope. If you have a hot neutron-rich environment, like in the aftermath of a neutron star merger, the color, by the way, is abundance. Then you have some set of isotopes that are actually not on the stable line here that are more neutron-rich than symmetric matter, that are in nuclear statistical equilibrium. The reactions are in equilibrium with each other, but as you let this material expand and cool, it captures neutrons along the bottom here, so-called neutron drip line, until you run out, and then you radioactively decay back to stability. And when you radioactively decay back to stability, this produces a lot of heat, and it glows. The color of that glow depends on the elements that are fused. So this bottom panel here now is sort of a 1D cut of this. So the x-axis now is atomic mass, and the y-axis is either abundance or mass fraction. And if you have this region that I'm pointing at here, it's called the rare earth peak, that's opaque to visible light. And so if you have a lot of this stuff, or even relatively little, but enough of this stuff, you'll get a redder glow because photons will be reprocessed as they pass through this material before if they're too high frequency. On the other hand, if you have less of this stuff and more of, say, the second peak here, the second R process peak, then you'll have a bluer glow because photons won't be reprocessed to longer wavelengths. And in 2017, we saw this. So this is a composite image from the Swope and Magellan telescopes. The left panel is the day of the event. The right panel is 4 days later. The big blob in the center is the host galaxy. And the thing the arrow is pointing at is the afterglow, so-called kilonova, from this radioactive decay. And on the day of the event, it was sort of bluish green. And 4 days later, it was red. And what this suggests is that there were at least 2 sites of our process nucleosynthesis that produced at least these 2 different kinds of compositions, one with more lanthanides, the rare earth peak, and one with fewer. And just to give you a sense for the timescales here, this is sort of the path of all the relevant processes. The in-spiral of 2 neutron stars, it takes a very long time, obviously, but it's in the LIGO band for about 30 seconds, of which only the last few orbits need to be captured with numerical relativity. But the relevant timescale here that you have to capture is roughly the light crossing time of the system, say of a neutron star, which is order microseconds. After that, you get this long-lived remnant and neutron-rich accretion disk that is driving a wind. And the timescales here, the disk will drive a jet, perhaps, that lasts seconds, as Elias talked about. But the timescale you have to capture is still about a microsecond. It's still the light crossing time of the system. The nuclear reactions, fusion happens quite quickly as you climb this neutron drip line, but then the radioactive decay happens over a wide range of timescales, which has to do with the half-lives of all the elements that you're passing through. So the timescales you have to capture is sort of logarithmic. It ranges from seconds or fractions of seconds to hours to millions of years. And then if you want to figure out what this looks like on Earth, then you have to capture the timescales of weeks having to do. The kilonova actually has 2 phases. There's a photospheric phase, which lasts, excuse me, days. And then there's a nebular phase, which lasts weeks. And this has to do with sort of the optical depth of the material. And through all of this, neutrino transport is essential because neutrinos can control the amount of neutron richness in the material. When you emit a neutrino, if an electron neutrino, you change the composition. For example, in beta decay, a neutron decays into a proton, an electron, and an electron antineutrino, for example. And to show you this, I have this sort of toy example that I put together here. This is a gas in sort of neutron-rich neutron star merger conditions. The color map here is YE, which is electron fraction. Lower YE means more electron slash proton. Low YE means more neutron rich, less proton rich or electron rich. YE of 0.5 is symmetric matter. That's sort of us. YE of above that would be more proton rich than neutron rich. And I've set 2 boxes here with slightly different electron fractions, one with a little bit more than the ambient, one with a little bit less. And I've freeze the fluid so that material cannot travel in or out of these boxes, but neutrinos can travel freely. And so when I run this calculation, neutrinos carry the electron fraction from the neutron-rich region to the neutron-poor region so that everything comes into equilibrium. And if you're very sharp-eyed, you may notice that the background color of the movie also changes a little bit. And that is because the neutrino field itself is carrying some amount of conserved electron number. Of course, I just told you electron number is conserved, but it's only approximately conserved. And that's because neutrinos can transform from one flavor to another. So back when there were a bunch of neutrino experiments observing neutrinos from the sun, it was discovered that the number of electron neutrinos that were observed in these experiments was much less than expected. And that was because after electron neutrinos were emitted from the sun, before they reached Earth, they had oscillated, they changed into other flavors of neutrino, which means that the total lepton number, i.e. number of electrons, muons, and tau is totally conserved. But the electron number is not. An electron neutrino can convert into a mu neutrino or a tau neutrino. It's also, this is understood as coming from the fact that the mass eigenstates of the neutrinos are not the same as the flavor eigenstates. And so given the mass eigenstate is the one that is fundamental, a given neutrino is of a single mass is actually in a superposition state of many different flavors. I'm not going to go into those details very much, but I use this to motivate the fact that there are, in hot, dense environments, the neutrino flavor can undergo instabilities that have to do with the neutrino field self-interaction and interaction with the ambient matter field. And there's a number of these kinds of instabilities. One of them is called the fast flavor instability. And the time scale for the fast flavor instability is absurdly short and the length scale also, compared to the length and time scales of a neutron star merger. The time scales are roughly nanoseconds, and the length scales are roughly centimeters, compared to a black hole radius of order kilometers and the light crossing time of order microseconds. So it's absurdly small compared to the time scales we actually need to capture. This means that it's basically impossible to treat the fast flavor instability from first principles, but there's been a lot of progress in the community by a number of groups, not just mine, towards doing this sort of in situ in simulations with subgrid modeling or proximate heuristics. One heuristic that was suggested by Zaisen and Nagakura has to do with this crossing indicator function that I've written down here, which is, it says that when this crossing indicator function crosses 0, and by the way, this is the number density essentially in phase space of electron neutrinos minus electron antineutrinos, minus 1/2 that for, so x here is either mu or tau, but not both. So the 1/2 is to specify, well, x is the sum of mu and tau. So 1/2 is supposed to signify either mu or tau, but not both. It's very common in these kinds of models to group the non-electron neutrinos, i.e. the heavy lepton neutrinos, into a single bin because they don't influence electron fraction. So that's what's happening here. Oh, sorry. When this crossing function crosses 0, that indicates that the fast flavor instability has triggered and the neutrino field is going to change. Zaisen and Nagakura suggested, based on a bunch of microphysics simulations that they did, i.e. first principles models, well, there are details there that I won't get into, but essentially first principles models of a very zoomed in neutrino system. And they found that that when the crossing indicator function crosses 0, the neutrino field changes to eliminate that crossing. So this is what I'm showing here on this left panel. You initially have the blue curve, and after the instability saturates, you have the orange curve. And what's happened is that we've moved enough neutrinos. Electron neutrinos can go into heavy, but they can't go into antiparticles. So you can go from a particle can go to a particle, but an antiparticle can go to an antiparticle, but a particle can't go into an antiparticle. You move enough neutrinos from one flavor state to another in such a way that the total integral of this crossing indicator function is conserved. But and what that means is you essentially eliminate the region of smaller integral, and you transform that function so that the total integral is conserved. And the impact of this on the electron and the heavy neutrinos is shown here on the right. So we implemented this in our Monte Carlo transport code NUBLIGHT, and you might imagine that to do this, you actually need angular information about the neutrino field. So this x-axis here is not space, it's direction of travel. So you need that, and so you need a very detailed picture. It's not enough to have an approximate formula, which you might get from, say, an M1 closure scheme for a moment method. You have to do real transport to capture this. So we implemented this in our code NUBLIGHT, and what we found is that the fast flavor transformation would essentially, because we would have electron neutrinos that would be emitted and then transform into mu or tau before they were reabsorbed, the opacities for the mu and tau neutrinos is much lower. And so the disk would essentially much more efficiently cool with oscillations turned on. And this is a movie of temperature where the x-axis, or sorry, the left panel is a colloidal cut. The right panel is equatorial. This was a 3D simulation. And the color bar is temperature here. And on each panel, the left is no oscillations, the right is oscillations. And you can see that the disk is much cooler in the oscillations case. And just to show you that this is actually working, Here are different points on the simulation where we have looked at we've picked some point in the simulation, and then we've looked at the crossing indicator function as a function of direction of travel. That's what this mu is. And the red and the blue or green are different simulations. One of them had oscillations in it, the other did not. So these are not like a before and after. That said, it's actually remarkable that they look so similar. The oscillation simulation, the crossing indicator function, just looks like as if the instability had taken the indicator function with the crossing and removed the crossing via the fast flavor. So this is actually, I think, remarkable that these agree so well, and it's comforting to demonstrate to us that our scheme is working as intended. This has an impact on the outflow. So what the major impact here is that if you are not absorbing as many electron neutrinos, two things happen. One is you have less heat to drive a thermally driven wind off the disk, and the other is that that thermally driven wind, to the degree that it is still driven, is going to be more neutron rich, because electron neutrinos that were being emitted from the accelerator and absorbed in the corona, they're no longer being absorbed, and so you don't re-leptonize the outflow. And this is what we found. Okay, I'm going to pause here before I go into the next section of the talk, which is going to be on the details of Monte Carlo transport. So those of you who are paying attention for the astrophysics, ask your questions now, and then you can go to sleep or go to lunch. Those of you who are interested in more technical details of transport methods, I'm about to speak to that. Okay, no questions. Zach, by the way, please keep an eye on questions. I'm monitoring the chat, but please keep an eye on people asking questions or raising their hands in the room. I'm happy to pause anytime if someone has a question in the middle.
No problem, Jonah.
Okay, great. All right. So now to completely switch gears here and talk about Monte Carlo transport, first I want to argue for you, if someone hasn't yet, why transport is hard. And the reason is that or harder than, say, the hydro equations or the Einstein equation, differently hard than the Einstein equations. And the reason is the number of dimensions. So the fluid equations say the density depends on only 3 spatial dimensions in time. So if you break up a hypercube into points, then the cost of that is the number of points per axis to the 4th power, like the grid spacing to the 4th power. On the other hand, the transport equations depend on 3 spatial dimensions and 3 momentum dimensions and time. You care about not just where you are, but also where you're going. And what this means is that you have a 7-dimensional hypercube you have to break up. And so the cost is then your grid spacing, one of your grid spacing to the 7th power. So the same resolution simulation is much more expensive. And this is actually what motivates Monte Carlo methods. Monte Carlo methods have an error that scale. They're a particle method and a fundamentally statistical method. You assume a distribution function that's essentially a sum over Dirac delta functions that are weighted in some way. In my method, the weight is for a given particle is exactly the number of physical particles that a Monte Carlo packet represents. And this means that it's only meaningful if you integrate over f, which, because they're delta functions, integration just becomes summation. But it's a fundamentally statistical method. I actually disagree with the argument that was made this morning that you could, if you were just worried about transport, then you could get the without matter radiation source terms. If you just cared about solving the geodesic equation, you would get the exact right answer with only one packet. That's true if you only care about one neutrino beam. But if you care about all paths, then it's still a fundamentally statistical method, even if you don't have any random sampling in the deterministic part of the method, which is where you're doing where you're solving the geodesic equation. If you care about having a picture of the neutrino field, you always, in some sense, it's only meaningful under integration. But the nice thing is that the error scales as 1 over the square root of the number of particles. It squares as shot noise. And this is great because it doesn't scale with grid spacing or with the dimension of the problem. There is no grid. And so this cost is the same whether you're solving a fluid or whether you're solving a Boltzmann equation. That means that for small dimensionality, this is worse, and for large dimensionality, it's often better, with some caveats. Interactions with the gas are probabilistic. So I'm going to go into some details about various pieces of the method. So for example, when at every time step, you decide how many particles you want to create, and this is you get to choose the number of particles you want to create, but then the weight per particle is set by the integration over the emissivity. So that's what this top equation here is saying. So this is the number of particles to create at a given time step is given by the time interval times the sum over flavors. F here is intended to be the number of types of species, times the integral over the volume of interest in phase space. So this is space and energy and direction of the total number of particles that are expected to be emitted from a physical perspective. Epsilon here is energy. So you choose how many you want to create by taking you pick how many you want to create, you set this W by performing this integral, and then to actually per particle pick what's happening, you sample the emissivity as if it was a distribution function. The weight actually doesn't have to be constant across particles, so long as you choose a closed form for it so that you can solve. So for example, in my code nublight, we choose one that samples high energy neutrinos more finely. So the weight for a given particle is given by essentially it's inversely proportional to the energy. So you have smaller weights and thus you need more particles in the higher energy regime. And then C is a constant that's set by this integral. Scattering and absorption are also probabilistic, but the one thing I want to emphasize here is something called biasing. So the point here is that you have to sample the relevant interaction as if it's a probability density function. So again, you compute some probability for absorption that's based on the optical depth, and for scattering some probability for scattering that's based on the scattering optical depth. And then what the result of scattering is you sample the cross section as if it were a probability function. However, so long as the integral works out, you can mess with these probabilities. So this is what's called playing a fair game or biasing. And so for scattering, this is what is commonly done. And you may want to enhance or de-enhance different processes. This is actually what allows, for example, Francois Foucault's code to run inside the interior of a neutron star. In nublight, where we're just working with accretion disks, which are more optically thin, I actually enhance rather than de-enhance scattering such that I will sample all the different scattering processes, because some scattering processes might be much weaker than others. And so this plot on the right here is showing applying this biasing scheme, where the red curve is the filled blue is an analytic distribution of what should be resulting from a beam of particles scattering off of a gas. The green curve is what you would get if you don't bias sufficiently well, and the red curve is what you get with nublight with the more sophisticated biasing treatment. One thing I want to note here is that when you do this, to make the probabilities all work out, you have to split particles. So when a particle comes in and it scatters, some fraction of that particle continues on with some reduced weight, and you create a new particle for the scattered particle with some weight. So the particle splitting is required to make this work. As I've already just inferred, and as was discussed previously this morning, particle paths themselves are actually evolved deterministically. You just solve the geodesic equation. We don't know what the neutrino mass is. We just know it's very small. So I and most other groups just assume neutrinos are massless, which is good enough for our purposes. One other thing I want to mention is a resolution requirement that can happen, which is that a packet, each neutrino packet carries a finite amount of energy and momentum. The energy, for example, being given by the weight times the energy of that particle, the energy given the frequency of that particle, like the per photon or per neutrino energy. If that energy is greater than the energy in a cell, i.e. if you integrate over the volume of a cell of the energy momentum tensor, if the particle energy of an emitted particle is greater than that, then you're going to end up with negative energy or zero energy in that cell. This is called supercooling, and it's an instability. It'll crash your code. So there's two solutions to this. One is to fix the time steps. So this is to say that you want to take time steps that are shorter than the relevant cooling or emission time, or you want to treat this implicitly. One of the two. My code just takes small time steps where you set the time step to be less than the physical cooling time, which is, say, the energy per unit volume divided by the emissivity. And you set this to, you essentially introduce another CFL factor that's of relevance here that's less than 1. There's also a number of particle requirement here, which is a quality factor that I defined in a previous paper, which is to say the number of particles created in a given time step over the entire domain times this cooling time, so ddt times tau, you want at least 10 particles created per cell per cooling time, essentially. That's what this quality factor really means. This is a stability requirement, and this is really tied to your mesh. This is what ties the particle count to the mesh for the fluid solver. And so this is why people talk about number of particles per cell. You need to have something like this satisfied. I actually typically target a total of 10 particles per cell, but that turns out to be way more than is necessary to satisfy this quality factor. But it is important for well sampling things like the fast flavor instability that I was describing before. Particle count is something, if you want to say you have some number of particles per cell, well, you have to pick how to balance that. So as I mentioned, every time step you create particles based on emission. So you want to create a number of particles such that they're balanced by the number of particles that are lost. And so this is something that you have to track throughout the code. You track how many particles are created due to emission and due to scattering. You track how many are lost by passing out of boundaries, like they leave the domain or they fall into the black hole. And you track, and then you compare these, and you want the number of created equal to the number lost when you are at your target number of particles. And so the equation you want to be satisfied here is essentially, is the one that I've written here. Created minus lost equals some safety factor times the target number minus the number that you actually have right now. i.e., if your target is greater than the number that you have, i.e., you don't have enough particles, create more than you lose, for example. So you have to have some dynamic control system, essentially, in your simulation to stay at the particle count that you desire. And obviously, things can go wrong if you don't do this well. If you have too few particles, like fewer than you expect, then the supercooling can hit you. And if you have way too many particles or way more than you expect, then you'll run out of memory or your code will run too slowly, et cetera. So it's important to get this right. And it can be quite painful to get these settings correct. Okay. One other thing that's useful to know is that interactions are much more easily expressed in Minkowski space, where the algebra is simpler. So to do that, it's the best way to handle this is to sample those interactions in a relevant rest frame. So you transform from the lab frame into the fluid rest frame, i.e., where the time vector is the forward velocity of the fluid, and then you have to pick 3 spatial vectors that are orthogonal to that. One, in an MHD simulation, I choose the magnetic field 4 vector. You can choose other things if you like. The other 2 are essentially arbitrary. So in Nublight, we pick a random one that's orthogonal to these 2, and then the third is essentially set by orthogonality from that. You have to do an additional transformation for scattering. You want to be in the rest frame of the scattering interaction, which means that you have to sample a scattering particle that you're going to scatter off of. So you sample from the Maxwellian distribution of the fluid for, say, electrons or protons or heavy ions, something like this. Okay. If you want to play all these games, one way that you could get a sense for how to do this is in my code, Nooblight. Here is a phone number for you if you're interested in looking at the open source code. It's low-level C, but there's it's a full open source implementation that you can reference if you're interested. I'm about to jump into some more lessons learned-y things as opposed to the recipe. So now is another good time to pause and see if there are any questions.
Any questions?
I have a quick question about the safety number that you mentioned, and you said it's dynamic. Does that mean it's just like you're changing it during the simulation, or how do you determine the value?
The safety factor here, Q, you mean?
No, I think it's a F when you.
Oh, F here. Yeah. So F is a parameter that one fixes, I would say. You don't let F change. The other terms in this equation are allowed to, well, the target number presumably also doesn't change. So F and NT are fixed, but NR and C and NL are allowed to float. So the way that I choose F is I basically say that I don't want to increase the particle count in a given time step more than, say, 10% or decrease it more than 10%. So F is actually a function based on whether you're increasing or decreasing. So it's essentially either 1.1 or 0.9. Like in this formula, I think it's essentially 0.9.
I see. Thank you.
Okay. Anything else?
Any other questions? All right. Seeing none, please continue.
All right, great. So the first thing I want to mention is in opacities. So my code Nooblight is what's called continuous energy, meaning each particle has a fixed energy, but the energies that each particle are allowed to take are free floating. What this means is that when you sample, say, an opacity, you are sampling a function that depends on density, temperature, electron fraction, and energy. If you sample that per particle, and you have, say, 10 particles per cell, that means you're doing 10 evaluations of a table lookup, for example, per cell, which is 10 times more than you have to do, say, EOS calls. This can totally dominate your runtime. And so an important trick here that is in Nooblight, for example, is to first compute the cell-centered values of the emissivity or opacity as a function of energy, and then evaluate that per particle. That means instead of doing, say, 10 lookups of the full 4D table, you do 10 lookups of a 1D table and one 4D table lookup per cell. So it's much more, well, 1 times n energies lookups per cell, which turns out to be much cheaper. Another thing I wanted to talk about is log spacing of tables. So this is true for emissivity and opacity, as well as equation of state physics. So most of us, I think, are using log space tables, say, for our equations of state, for those of us who are doing finite temperature nuclear equations of state. Typically, this is something like pressure and energy tabulated in log density, log temperature, and YE, for example. And the reason that we do this is because the logarithms span the huge dynamic range we need to capture, say from 4 to 10 to the 4 to 10 to the 12 grams per cubic centimeter in density, for example. And also, the relative spacing is roughly scales with the magnitude of the variable, right? So like delta rho is like the distance between 2 grid points in density is roughly proportional to the density. This is how logs work. And also logs are exactly invertible. So you can transform between a logarithmic space and a linear space very exactly. So you don't lose anything when you do this transformation. However, logs have a big problem, which is that they're very expensive. They're transcendental functions, meaning they can't be evaluated as a finite set of algebraic operations. They're a series expansion. When you say that you want to evaluate the logarithm of your density at double precision, that means that you are taking a series expansion of logarithm with enough terms such that the error of that expansion is less than machine epsilon, for the rounding approximate error for the precision that you chose. So that's painful. So one idea that we had was, well, actually, it's important that you have an exactly invertible function. And it's important that you have this property that deltas are roughly proportional to the size of the magnitude of the variable. But it doesn't have to be exactly proportional, and it doesn't have to be exactly a logarithm. You can get away with something that's only approximately logarithmic. And so our idea for doing this, we called not quite transcendental functions. And the idea is to use a floating point number, which has a structure. A floating point number is represented as essentially as scientific notation, but in base 2. So a given number n is a mantissa m times 2 to some power p, which means that if you take the logarithm of that number, you get the log in base 2. You get the log base 2 of the log base 2 of the mantissa plus that power p. So if you can approximate that, if you can find something that's exactly invertible, that's an approximation to the logarithm of the mantissa, which ranges from 1/2 to 1, you only care about that domain, that agrees at 1/2 and 1 and interpolates between them, then you have constructed an approximate logarithm. One, for example, would just be the second order interpolating function that satisfies these properties. So this interpolating function I've written here, log O2m, i.e. second order not quite transcendental, is this function has the properties that at 1/2 it agrees with the true log, and at 1 it agrees with the true log, and that the derivatives at 1/2 is twice the derivative at 1. You wouldn't think that you have enough constraints to enforce this, but you do, just because of the particular structure of a logarithm at second order. So it turns out you can satisfy all those degrees of freedom with, or all those constraints with only 2 degrees of freedom. And this turns out to work extraordinarily well. I'm not going to show you the code because it's kind of a mess, but if you're interested, you can take a look at follow this QR code. There's an example and reference implementations there. This is an improvement on a previous idea that we published some years ago, but this was done in collaboration with Peter Hammond and Jacob Fields out of David Radice's group. They were the ones who came up with who did a lot of the work regarding this and had some of the innovations. And one thing that I like to say about this, because it's just kind of a fun fact, is that this method is like very closely related to the infamous Quake 3 fast inverse square root, which some of you may have heard of. So it's kind of a fun connection to video game and programming history. And just to show you that this works, here is this is the equation of state for not a nuclear equation of state, it's actually copper. But the left panel here is the pressure of copper as a function of density and temperature in a log space. The reason that there's white in the middle there is because in that region, copper is in tension. In other words, the pressure it exerts is negative. It's pulling itself to hold itself together at those densities. The right 3 panels here are the errors of different approximations. So the right panel is the approximation if you do a table interpolation on true logs. The middle is the not quite transcendental logarithm at second order, and the left middle is first order, which is less accurate than the formula I showed you. And the not quite transcendental version is the errors are very, very small, even compared to the true log. And it's also, in many cases, much faster. So this is a plot of speedups. So the higher the bar, the better. The top row is the faster but less accurate version of this method. The bottom row is the more accurate version. Different bars are different architectures. And the left panel, the left column is a portable implementation. And the right column is one that uses like the fast inverse square root. It's bit hacked essentially version, something called integer aliasing. And the thing I want to highlight to you here is that in some cases, the speedups are quite dramatic. So on Intel architectures, for example, you can get something like a factor of 3 speed up with the integer alias second order method. One kind of, yes, Eric.
Did you test CUDA as well, or GPUs?
Yes. So I don't know if you can see it, but to the right 3 bars
Oh,
are.
I see it now. Thank you.
Yeah.
Yes.
So I was gonna mention that actually. So weirdly enough, on GPUs, taking logs with our faster method with not quite transcendental doesn't seem to be any faster, but it's still fast. But exponentiation, i.e. the inverse, which you do need to do, is faster than the system calls. I don't fully understand this, other than that GPUs are much more likely to be memory bandwidth rather than flop limited. So maybe that's what's going on. Another interesting thing here is that Apple system, ARM architectures, in particular NVIDIA Grace and say the Apple M2, our method is actually slightly slower than the system calls. And the reason for this is that ARM has a hardware log and hardware exponential. Actually, in the microcode for Intel, there is also a log and exponential, but it's software emulated in the microcode. Whereas the ARM architecture, there's actually a chiplet that does this. And so we can't beat that. Okay, so actually this is, I'm jumping once more to the second piece of lessons learned. Any more questions on this section?
I'm not seeing any hands.
Okay, great. So this is a very brief soapbox. So the reason I wanted to talk about this is that part of what I have been working on for many years at this point, in addition to my collaborators, is an adaptive mesh GPU-capable adaptive mesh refinement library that we call Parthenon. You can think of it as RMREX or CarpetX, although the design is slightly different. Like those codes, we break our mesh into essentially uniform grids on which applications can be built, but the hierarchy of these grids and the way one traverses them is slightly different. We have an octree, whereas a traditional patch-based method doesn't necessarily. We implemented our performance portability, our GPU capability with Cocos, which is a performance portability library. And we also implemented tasking. So to handle load imbalance and different regions of space being more or less expensive, we can move blocks of data around and we can pick up work sort of greedily. This requires that you over decompose, so you have more blocks and more work per CPU or per thread on a warp than you have. Then you need more than one, so that you have some slack so that you can move stuff around. The problem is that launching one of these tasks, one block of work on a GPU, has a cost. Basically, every time you talk to the GPU, you pay a 6 microsecond latency as you have to go from main memory and the motherboard and your CPU system, potentially through a PCIe port to the GPU. And in addition, the GPU itself has a scheduler, and that scheduler can serialize, even though the GPU itself can obviously launch a lot of work in parallel. And so we found that when we first implemented our method with AMR, we basically found that GPUs were slower than CPUs, dramatically. And the reason was we were essentially entirely paying the 6 microsecond cost. That there was not enough work to saturate the GPU. And if you have lots of little kernel launches where you're launching work on the GPU and each one has a small amount of work, you're entirely latency bound. Our solution to this is to coalesce work across blocks of your mesh in sort of a developer programmable way. So you coalesce kernels across blocks, and then you can launch a big block of work. The price of this is that you're exposing less asynchronicity that you can take advantage of. So this is why in Parthenon we have it as a runtime tunable setting. So just to show you how much this can matter, I wanted to show you a plot of ghost zone communication, which is actually where this is. We saw this as the biggest issue actually, and there's you can only do so well in this problem because you have some. It's essentially a surface area to volume ratio problem. your ghost cells aren't doing real work. They're just there to make your method run. And so the ratio of ghost cells to real cells, if it's large, you can't overcome that. No amount of coding will fix the fact that you have more ghost cells than real cells. Nevertheless, this plot on the right here I'm showing is essentially a single mesh of fixed size, and then we've just changed the number of mesh blocks that break up this uniform grid, and this is the cost of only the communication kernel. So the y-axis here is the cost relative to just having a single block. The x-axis is more mesh blocks to the right, less to the left. Smaller is better here. The original curve is this dotted orange line, and that curve is what is basically just coming from ratio of ghost cells to real cells. As you, the original if you naively do GPU kernels, where you're launching one kernel per sort of region of the ghost halo that you have to communicate to different neighbors, you get this dotted blue line, which is absolutely atrocious. 100 times worse in some cases than the CPU code. As you add more and more buffer coalescence and increase the strategies for packing so that you can combine more work and launch fewer GPU kernels, you can actually essentially completely recover the CPU curve. And so this is something I wanted, the take-home message for this part of the talk that I wanted to share with you all is essentially that as you think about running on GPUs and porting your code, the promise of performance portability is essentially a lie. You have to think about the algorithm that's running on the GPU versus the CPU. And the ideal way to, in our experience, to make this work is to have tunable parameters in your code so that you can change the way your code functions so that your algorithm is more ideal for the different kinds of hardware that you want to run on.
Sorry,
Okay.
I have a question.
So yes.
Could you explain more what do you mean by pack buffers?
Yeah. So the way that we do communication in Parthenon is we take some region of the ghost halo and we serialize it into a 1D array that is then communicated through MPI or just copied to another mesh block. But we always do this because it makes the number of code paths smaller. So the branching here is whether I send this through MPI or whether I just do like a copy operation. But we always serialize each region of our ghost halo. That's what we mean by pack buffers. The other concept here is packing the kernels together. So we also talk about packing in that context. So in our code and in this plot, packing is sort of an overloaded concept. Pack buffers versus pack buffers and blocks here is the difference between per mesh block only fusing the GPU work for each piece of the ghost halo, or fusing the kernels such that there's only one kernel that walks through all the blocks and all the pieces of each ghost halo on a block. Does that make sense?
Yes, thanks.
Okay. Great. All right. So are there any more questions? I know I'm 10 minutes away from you and lunch, so I'm going to try to make it. If there's enough to talk about now, I'll just skip the last section. If not, then I will share with you what I see as sort of an interesting next direction for transport.
Not seeing any hands, so please continue.
All right, great. So Monte Carlo, all transport methods to some degree, their goal is to overcome what's called this curse of dimensionality. The fact that 7-dimensional problems are harder to mesh up and more expensive than 4-dimensional problems. That's what motivates Monte Carlo. It's also what motivates things like the moment approximation in the first place. So one idea that has been recently circulating that we recently explored comes from quantum mechanics, many-body quantum physics. And the basic idea here is to represent a high-dimensional array, say a 6-dimensional distribution function, as a tensor product of smaller arrays. So this is the representation I've drawn here. So f of ijk LPQ is some 4D array tensor producted with a 3D array, tensor producted with another 3D array, tensor producted with a 2D array. So this is a more compact, this is potentially a more compact representation. Note that what I've done here is this is exact. You can always do, well, you can often, not always, do this. And I haven't made any approximations or shrunk the cost yet. Where the shrinking of the cost comes from is the fact that the tensor product term, so the A here, the size of this index, the size of the B and then the size of the B index and the size of the C index. If these indices range over a small number, i.e. 7, as opposed to 100, then you've won, because then the cost of this method scales. By the way, the size of these indices is called the rank. The cost essentially scales as 4-dimensional instead of 6-dimensional, because you have it's the size of this tensor plus the size of this one plus the size of this one. So it's essentially the rank by 3D in this case, instead of 6D. If the rank is very large, say larger than the original dimensionality of the problem, you can still represent your solution, but you've lost. You could actually end up with a representation that's more expensive than the naive 6-dimensional representation. So one thing you might try to do is truncate the rank to satisfy some error tolerance. And this kind of looks like an arithmetic approximation in the sense that you've essentially said, I'm going to round my high-dimensional tensor to some lower-dimensional tensor at some rounding tolerance. And in that case, you can keep the rank small and you can control it. Or, well, the rank is allowed to free float, but it's hopefully not too large. And this can potentially allow you to run transport problems at absurd accuracy. So this is a standard test problem called the line source problem. Basically, it's a z-planar symmetric problem where you start with a pulse of light at the origin, and then it's allowed to move outward. And at a small number of angular dimensions, so the discretization here is space and then 2 angles, theta and phi, say, and then energy. This one is a gray transport scheme, though. Neutrinos can only travel along the angles that you've discretized. And so at a small discretization, that's 4, for example, it looks totally wrong. But even at standard sort of affordable resolutions like 16 or 32, it still doesn't look right. It only starts to look right at absurdly high numbers of angles, like 500 by 1,000, for example, in this case. And that's not something one can typically run. But we ran this in Python, in a Python code on our laptop. The speed up that you get and the goodness of your solution is a trade-off, and it depends on the rounding accuracy you choose. So on the top panel here is the same solution I just showed you. We've chosen a sufficiently good rounding accuracy. The bottom panel, the accuracy was chosen not good enough, and you can see that you get this sort of numeric ringing, and you get artifacts. The right columns here are showing the speed up compared to a traditional method based on various settings like the rounding tolerance, et cetera, as a function of the time step and the resolution. And the one I want to guide your eye to is this bottom right one, which is where we ran with a sufficiently high resolution that the angles actually came out. And at the beginning of the simulation, this is producing like 10 to the 7 speed ups. And at the end of the simulation, it's only a modest factor of 100. This is a test problem which I think I will mostly skip, other than to motivate that even for problems where you might think that this kind of thing doesn't matter, it actually does. So this is a test problem called the crooked pipe. And the idea is you shine a beam of, in this case, photons from the left, and they're confined to this pipe. And what happens is they hit the walls of the pipe and they heat it up, and then that light is emitted again. And so it's sort of a reprocessing. And even at modest angle cap, you might think that this is roughly an isometric problem, and that really you shouldn't care about angles. Well, it turns out you do, because the angle of reprocessing when you emit determines sort of the angular structure of temperature along the edges of the pipe. And so if you don't have a high enough resolution and angle, you don't get this problem right. Also, the right panel here is showing the rank of the for the two tensor products that are taken in this particular version of the method as a function of the time step, given the rounding tolerance. And you can see that the rank starts very high and then it shrinks. And so you can kind of think of this almost like adaptivity and angle or energy based on the structure of the method. So it's sort of like AMR. So that's another benefit, is the adaptivity. Okay. So I covered a lot. Like I said, it was kind of a grab bag. Hopefully you were all able to follow it. But to summarize, neutrino transport is hard and necessary. I think there's many low-level tricks that are required to get good performance and to get the right answer. New algorithms are still emerging, which I think is really exciting. I was asked at the last workshop, what transport method should I implement? Say, if I'm going to put this into the Einstein toolkit or into Asterisk or something. And right now, I would still suggest the guided moment scheme. Monte Carlo methods and moments are both individually useful, and they're steps on the path to a full guided moments implementation. I don't think the tensor method I just described is really production ready, but keep your eyes out. I think it's really exciting. And I also wanted to emphasize that neutrino oscillation are one example of where you really need full transport. It's not enough to have an approximate method. And first principle calculations are still impossible, but in-situ methods are increasingly common and interesting. And just here's a list of some other recent works of various ages where people are starting to really take this seriously. And I think that's very exciting. This is a physics problem that a few years ago, basically everyone said was impossible, and now people have decided to attack it. So that's very cool. Thanks.
Great, thank you, Jonah. We have a question here.
Yeah, thanks. I wanted to follow up on the point you made earlier in your talk about the latency issue on exchanging data on GPUs, and especially if you have to move really huge amounts of data between nodes and then go to the GPUs, you're going to get killed by the latency issue if you first transfer the data into the CPUs and then have to transfer into the GPU. Anytime you buffer on GPU nodes with the CPU memory, you're going to get killed by that latency issue.
Yeah, you're jumping. So no, this is even with this plot is forget MP. It's true you need this for MPI, but forget CPU host CPU resident buffers or GPU resident buffers. This plot is relevant for CUDA-aware MPI, and it has absolutely nothing to do with the amount of data that you send, and it has everything to do with the latency of sending instructions to the GPU. It doesn't even matter if you're copying data, because when you launch work, when you launch a CUDA kernel, you are copying the instruction set and also whatever relevant like stack variables you have to send. So this story holds even if you're not copying data back and forth.
Okay, well, the reason I wanted to mention this issue is because not on specifically Einstein Toolkit, but on another project we're working on, we're actually talking directly to NVIDIA about new tools they have to directly transfer data into the GPU memory using the most advanced development tools, like the latest versions of CUDA, and on the most latest type of GPU architectures, you can transfer data directly into GPU memory and bypass CPU memory using the latest NVIDIA stack. You can do this on the latest GPUs.
Are you referring to like the hardware shared memory, like on the Grace Hopper kind of it?
Yeah. So exactly. So on the Vista system here at TAC, they do have that on the H200s, and you can do that. You can transfer your data directly into the GPU memory, and so that's a great boost. That's a great help.
I challenge you to run the following experiment, which we ran on our own Grace Hopper system.
Okay,
turn on that stuff, and then still just launch 100 empty kernels, and you tell me how much time it takes. There's that's pretty significant latency.
I would say that's a very valuable thing. We want to try to benchmark this on the Vista system to see what happens when we test this out. So we definitely want to look at that and see what happens.
But you're right that this is getting better. So as the memory spaces move closer together, this issue does get better. So that's a good point. But I would argue that NVIDIA's claims that this is totally gone are overblown. We still measure the latency.
Okay, well, I'm glad you brought this up because, like I said, and I'd already talked to Steve briefly about this before this session, that we want to start testing this on the H200 GPUs on the Vista system here to see what kind of speed ups we can get and whether or not the stuff that NVIDIA is telling us, like you say, whether or not this turns out or not, we're going to want to test it and see if this really does make a difference.
Yeah, cool. That I'd be interested to hear the results of that.
Yeah, okay. Well, thanks for bringing up this issue because we really want to see what we can do about this with the new compile toolkits that NVIDIA's putting out. Like I say, we want to see if this really does boost things or not.
Yeah. Yeah, and full disclosure, we tried this on the H100s and the Graces. I don't know what it looks like for the H200s or like, Blackwells when they come out. Surely it will get better with time because this is a interestingly political issue, right? Because the reason that we don't have shared memory between GPUs and CPUs historically is because the CPU vendors didn't want to play ball. So APU systems like the AMD, what is it, MA300 or whatever, the MI300 APU as opposed to GPU is their equivalent, and we haven't tested on those either. So I think this will get better with time, but it's always important to be aware of the hardware you're running on, right?
Yeah, okay. Well, thanks for bringing this up, and we'd definitely like to follow up on this.
Great. So I'm not sure. Do we have time, Johnny? We're out of time, unfortunately, but yeah, sorry.
Okay. If you have questions, feel free to email me. I'm happy to answer. I wish I was there in person to talk over lunch, but I'm still happy to talk.
Yeah, and we're happy you did. Give us this very nice talk. Let's thank Jonah once again and all our speakers. There we go.